Hey everyone, my name is Kyle Markland. Hopefully you had a great lunch. Hopefully I caught you before the food coma sets in. I represent Multimatic, and on behalf of my colleagues at Multimatic and at Michelin, I want to share with you an update on our work using FTire for virtual ride development. There it is. I want to start by acknowledging that this body of work is a group collaboration between 3 different organizations. From COSIN, I'd like to acknowledge Benny Reef, who's our main technical contact there. From Michelin, I want to acknowledge David Fitzgerald and Yang Huang of the simulation department. And from Multimatic, I want to acknowledge Tony Yardley, Andre Alvarez, and myself as co-authors on this study. So Michelin is a tire company who I'm sure needs very little introduction. They're ubiquitous. The car I drove here today has Michelin tires on it, and I'm sure many of your cars do as well. Michelin is one of the industry leaders in tire design, analysis, and manufacturing. And more importantly for this study, they're globally recognized for their expertise in tire modeling. And it's for this reason that they are an attractive partner for the type of simulation work that we do here at Multimatic. That brings me to Multimatic, which is the organization I represent. We are a Tier 1 automotive supplier who delivers components and engineering services to the global automotive community at any volume level. This includes component level devices such as hood hinges, dampers, active mechanisms, all the way up to full vehicle niche programs. These niche programs are really cool cars. Some of them are the kinds that you would hang up on your wall on a poster. One such example is the Ford Mustang GTD. It's one of our niche vehicle programs that is based on the current generation S650 Mustang. And the whole ethos of this vehicle is to be a race car that you can drive on the road. And it's packed full of technical goodies, such as an inboard rear suspension, Multimatic's own adaptive spool valve damping, dual height and rate suspension system. And to top it all off, the tire sizes that this car wears are absolutely monstrous. So in the front, it has a 325 millimeter wide tire, and the rear is a 345. And it's the tires on this car that will actually be the star of our show today. So we partnered with Michelin for their Pilot Sport Cup 2R tire. If you're trying to make a road car go really fast around a racetrack and you have a specific lap time goal in mind, this is the tire that you want on your car. This is a semi-slick tire that is optimized for track performance, but somehow also happens to be road legal. And the most powerful machines on the road today, from the likes of Porsche, Ferrari, Mercedes-Benz, Koenigsegg, and Corvette, all use this tire in their high performance variants. And when we talk about tires like a Cup 2R, it's not necessarily a one size fits all monolithic product. There's an iterative tire development process that goes into optimizing the tire for the specific program. For the Mustang GTD, the vehicle work that we did in 2024 spawned several iterations on the tire's construction to meet the demanding needs of the program. And of interest in this particular study are 2 construction iterations, one of which we codenamed CC, and the other is a later iteration which we refer to as LN. So the LN tire was developed to meet some of those program goals, but it came at the expense of ride quality. So very early on in the program, when this tire was introduced early on, our development driver was giving us subjective feedback that the ride quality of the car was degraded with this tire, despite some of the other advantages that we sought to get with it. So Multimatic's simulation capability, and as well as the fact that we have a high fidelity gold Mustang GTD vehicle model, enable us to do virtual testing on our tires to close the loop on the subjective feedback we were getting from our development driver. And as a continuation of our tire studies that we were working on last year, which we presented at last year's Udine ZPS, we identified FTire as a tool to virtually capture the difference in the 2 tire constructions and to study their difference in performance on the vehicle. So that brings us to the scope of the work I'm presenting for this year, divided nicely between Michelin and ourselves at Multimatic. So the process started at Michelin, where they took their CC and LN tire constructions and measured them on their tire test rig in the lab. So if you've ever seen this work, really fascinating stuff. They basically load the tire in a whole bunch of different scenarios and load cases, and they use this data to then fit a tire model onto the empirical data that they've collected. And so that's the second step, is they generate an FTire model for both of the constructions of interest, and they pass those models along to us. When the FTire models are in our hands, Multimatic's responsibility is doing offline simulations to quantify the differences in the tires, using our ride metrics to characterize them, and finally performing a subjective evaluation on some of our VI grade simulators. In particular, we're going to talk about the full spectrum simulator. So let's just say a few words about virtual tire modeling. So one of the oldest, kind of most well-known tire models is called a magic formula model. This is a single point contact tire model. That is, we represent the tire contact patch with one point on the ground, and we fit empirical coefficients that describe the tire's friction properties in the various load cases given the conditions that it's in. And it turns out these are very good for approximating the limit handling behavior of the tire. However, the obvious limitation of using a single point contact is that tires are soft bodies that are filled with air. They can deform, deflect, and envelop around obstacles in the road. So in order to do a detailed virtual ride analysis, we need a more sophisticated tire model. And this is where FTire comes in. So this is a physical tire model that consists of many hundreds of points that are each joined with their own stiffness and damping terms to make a better mechanical model of how the tire actually works as it goes over obstacles, as you can see in the graphic here. So to say a couple more words about how the FTire model is implemented, the core mechanical model consists of two different parts. So the tire structure consisting of the bed, the bead, the carcass, and the belt is subdivided into 60, sometimes as many as 360 different segments that are connected to each other by their own nonlinear stiffness and damping terms, as well as pressure-dependent terms. The second part is the tread, consisting of 1,000, 10,000, sometimes even more points. So this is much higher density on the tread, which is meant to capture the tires sticking to the road or slipping, depending on the conditions. And so that includes nonlinear rubber stiffness and damping terms, and a friction coefficient that's dependent on sliding velocity, its pressure on the ground, and temperature. So this slide describes how Michelin performed the relative FTire fitting for the vertical dynamics work that we did. So they started with the CC construction as their reference tire. So it's a tire that they understood very well. The LN tire is the newcomer, and they want to understand these differences and then capture this in their model. So they use an FEA analysis to predict how the changes in modal properties of the LN tire come about from its construction. And for this, they specifically use a dynamic cleat test, and they're able to get all the information they need about the change in the tire's modal properties from this one FEA. So they get a delta in the tire's modal properties, and then the next step is they will fit an FTire model with the knowledge that they have about the delta between the LN tire and the reference CC tire. Then they go through the traditional FTire fitting process, and the very end is a validation to make sure that the FTire model that they fit has a good agreement with the findings that they found in the FEA in the first step. It's really quite an impressive process. And of course, no virtual tire will be complete without a virtual road to drive on. So here at Multimatic, we like using Coolidge Highway as one of our reference ride surfaces for our vertical dynamics work. This is a road local here in Troy, Michigan, and we've run many cars across it in instrumented states. It's a road we understand very well. But in addition, we've also laser scanned this road and basically made a digital replica of this road that we can drive on in our simulations. And so the process of that looks like driving down the road with a LiDAR attached to the car, scanning the road at millions upon millions of discrete points, and then taking the many gigabytes of data that you get off of that. There's a processing to turn it into VI Grade's grid mesh implementation, and you eventually get a road surface with a resolution of 0.01 meters. So it's a very fine road surface, and that level of fidelity is necessary to get a good correlation to the results that we would see driving the car in real life. And so how did we do? Let's get into some results here. So everything we're going to see on this slide is on-road vehicle data, and we like to use PSD plots to describe the ride comfort of a vehicle when it comes to vertical dynamics. And the PSD basically shows you on the y-axis, it is the power of a certain signal, and on the x-axis, it's the frequency. And so this is a good way to kind of objectify the things, the vibrations, the body motions that you're feeling as you're driving down the road in a car. And on the left, we have vertical acceleration, then roll acceleration, and pitch acceleration are 3 different modes of interest for our work. And this is a comparison of CC tires in orange versus LN tires in blue on the real car on a real road surface. And I want to draw attention to the fact that these look very similar. And one of the interesting findings in this study is that objectively, it looks like there's a small difference in content between the tires. It's particularly noticeable above 30 hertz in the higher frequency. However, if you get a driver in the car, a human is an amazing filter at picking out the differences in these tires, even though they might look small objectively. So to kind of continue that discussion, we have our metric called road texture transmission. It's one of Multimatic's validated objective metrics, which basically describes how much of that road surface gets conducted up to the driver. We're literally quantifying an accelerometer placed on the driver's seat rail to figure out how much of the kind of acceleration from the road percolates up through the vehicle to the driver. So we're looking at the vehicle as a transfer function here, and the tire as a forcing function. The top 2 set of graphs are the simulation data from our offline runs, and the bottom 2 graphs are the real-world data. On the left, it's the PSD plot, which might look familiar. It's a similar format to what we had on the last slide. And the right is a comparison of the ride metrics. And in the simulation, we were able to capture a directionally correct difference in the road texture transmission when moving from the CC to the LN tire. That is to say, the LN tire is stiffer and conducts more of that road texture to the driver. However, as you can see, the difference between the 2 tires in the sim results is much smaller than it is in the real results. And so to continue this work, we could do an additional iteration step on the fitting of the LN FTire to try to capture a larger delta between the 2 tires like we see in real life. So there's an iterative component to the tire model development. And finally, we wanted to close the loop on the comments that we had been getting from our development driver with a subjective evaluation. As I mentioned before, the differences in the objective performance of these tires is very subtle, but it's very easy for a human driver to pick out the differences. Humans are very sensitive to these types of content. So we actually used our VI grade FSS, or full spectrum simulator. Some of you may have seen it's in the room right on the other side of this wall. This is a ride dynamic simulator capable of reproducing the full frequency bandwidth of the vehicle response from 0 hertz, so that's including body motions of the vehicle, tactile range, all the way up to the very tippy top of the audible range at 20 kilohertz. So we performed a back-to-back comparison of FTire models representing the CC construction and the LN construction with our development driver in the loop on our virtual Coolidge highway. And this is what our development driver had to say. He said the LN tire feels more aggressive vertically, definitely more vertical activity in the vehicle. There's more choppiness, there's more mid-frequency. And that the driver was definitely able to perceive a difference between the 2 tire constructions on the simulator, and that difference is directionally correct, which means that this confirms the on-vehicle observation that the LN tires are stiffer vertically than the CC tires. So we recovered that piece of subjective feedback that we were getting on the vehicle on the simulator. So next steps, potential ways we could continue this work is to develop a faithful transfer function representation of our Mustang GTD vehicle model. Right now in our simulation, we're assuming rigid body. Obviously, we know vehicles are not totally rigid bodies. They act more like complex transfer functions. We're also excited to prove out the soon-to-be-delivered HyperDock and to kind of dive into its full spectrum capability here on our DiM250 in the coming months. And we're also looking forward to the delivery of an AutoHawk system. The additional computational horsepower that we'll get from that will allow us to run a higher fidelity FTire model and continue our work there. And with that, I would like to thank you all for your time and attention.